So this is a question that says outline the syntheses of each of the following from diethyl malonate and any other reagent. So this is 18.22b. So one of the things we do, since they say start with dimethyl malonate or diethyl malonate, it'd be the same either way. We want to try to figure out where does this molecule fit with dimethyl malonate. So if we're going to do the malonate ester synthesis, eventually we're going to be alkylating this molecule somehow, and then we need it to end up with these types of carbon chains. Along the way, we're going to end up losing this entire fragment. So really, for the malonate ester synthesis, it's only a 2-carbon building block. That means the molecule that gets in, the part of the molecule that gets incorporated will probably just be this portion, and we can try to map it out here. That means we need to be adding some new molecule in the alkylation event that will let us get to an alcohol. There's a couple different ways to probably solve this problem. I think the answer key would recommend you do an alkylation, and so I will go through this possibility. So always the first step will be deprotonating it. We're going to make, I'm going to use dimethyl malonate. I always end up drawing methyls anyways. I can't make myself draw an ethyl. So we'll get to the enolate. And the kind of tricky part here is we can't actually, this type of alkyl bromide isn't that great, because whenever you treat this with base, it quickly goes to an epoxide. And actually an epoxide is a reasonable electrophile for this, but we didn't discuss an epoxide in class. And I'm trying not to bring too many new nucleophiles in for you to consider in these problems to kind of narrow down the scope of this section. So if we want to use just a normal type of alkyl bromide, we could think about the starting molecule being in a different oxidation state. So we can imagine somewhere along the way, we're going to need to reduce this alcohol, so perhaps we could be reducing the other side as well. So instead of using this, we could use something else that'll bring in the same number of carbons. And this could be an alpha bromoester. So this would be able to alkylate this bromide. It would go down. And now we've added in the carbons that we need. We've now added in these carbons and oxygens. Oops. We're going to have this left over from the other molecule. Now we can kind of see where this is all going. So we need to use aqueous acid and heat to hydrolyze both of the esters, and then eventually do the decarboxylation. So this leaves us with a bis carboxylic acid that has 1, 2, 3, 4 carbons, and we need to turn this into a diol that has 3 carbons. And we can do a reduction reaction with lithium aluminum hydride, followed by adding in acid to protonate the alkoxides. So these are the same thing. This is the product. So a lot of these, it's trying to figure out what is the appropriate electrophile to add into the malonate to make the corresponding thing on the other side. For number 11, the practice exam. What happened to the OME on, if I remember my phone? I will go back to that and look right now. Since there's a number of these in a row, I will ask. What happened to the OMe group on the very left when the 5-membered ring is formed? So are you asking about going from essentially what happens in these arrows here? Yes. Okay, I can draw this out a little bit more explicitly. I'm going to copy and there we go. So after this attacks, where there's a intermediate in between. So we're going to have the ketone here. This will make a tetrahedral intermediate. We have the methyl over here. And from this tetrahedral intermediate, this will be able to collapse and give us that structure. Yeah. There's a question above. The question is, why does the double bond in the enolate attack the halide carbon instead of the carbonyl carbon? So there's, I guess, a couple reasons. One of which is these types of malonate enolates are actually very resonance stabilized. They're not very reactive. And because of this, they're not reactive enough to attack an ester. So this is one of the limits of the reactivity, and this is why we frequently see these types of groups being the endpoint in a lot of like Claisen type reactions, where you attack the ester, you kick out methoxide or one of the alkoxides, and you make a really stabilized enolate that can't do much else, or at least it can't react with any of the other esters around. So in this case, it has the choice of reacting with this actually very activated bromide. Since we have this electron withdrawing group next door, it makes this carbon that's being attacked in the middle, that I'm showing in red, very electrophilic. So this ends up being the best match overall. Cool. All right, I'll just keep moving along. So the person asked to try to focus on ones that'll help you guys out the most on the exam. I was not going to do this because I can't, I guess, tell you what's on the exam or not. But this is one that I would say is going to be a little bit removed from what we know. There is a way to do it with what we've learned, but the best way to do it probably involves alkylating an acid chloride. So I'll draw it really quick just for reference. Another way that I didn't introduce just to cut down time is something that I think you would agree would make sense. But it would be doing an enolate addition into an acid chloride. So you could make this enolate from something like LDA and the corresponding aldehyde. And once these add in, these acid chlorides are very reactive, so you can do the crossed addition. I may have lost a carbon on the other side. You can make this intermediate that'll quickly collapse and then give you your product. Since we didn't talk about acid chlorides much, and that is really the best thing to use here, esters would actually have some problem as an acyl donor. I would say don't worry about using acid chlorides. You won't need to do that, at least in the context of enolate chemistry. Enamines can still react with acid chlorides, though. That is something we learned and enlisted. And they would go through a similar type of process. Back to number 11. If you have an equal, so this is referring to number 11. The question is, why is deprotonation irreversible for the favored product? The favored product is a 1,3-dicarbonyl. It's a keto ester. And so if you compare the pKs of like methanol to a keto ester, the equilibrium will be hugely favoring the deprotonated state. And this essentially leaves it all in that form, and it doesn't really let the reverse reaction to get back into equilibrium and find its path towards other products. And the other products end up being much more reversible, and they'll just all funnel eventually to that deprotonated stage that is low energy. Yes. Unless you have contacted me to make some other accommodation, that is when the times are. Also, in number 11, why did the OMe group leave in the intermediate that you drew? So you're asking about this step? So this is, I would say, any time you have a tetrahedral intermediate that has a methoxy group that can leave, a methoxide group, you should at least explore that option. Formally, could be reversible at this stage, but if you consider the pKa of an enolate, so these are usually around, or of a ketone, that's around 19, whereas if you have something like methanol, it's about 16. Really, methoxide is the best leaving group from this tetrahedral intermediate. Hemiacetals aren't stable, so they're going to collapse one way or the other. And the other added benefit is once this actually goes and closes, you're going to very quickly have methoxide deprotonate the beta ketoester. And this is the form that is now very stabilized where it gets stuck. Oh, this is a 1,3-diketone. That means it's even more stable than a beta ketoester. Oh yeah, we can do 12F again. Let me see. So this is just like any aldol reaction. I think it's more difficult because it's just hard to keep track of some of the positions, keeping track of where everything is reacting. So in this molecule, you can make two different types of enolates. So this will react. Let's imagine we deprotonate one of the hydrogens. We could make this enolate. Or we could make another enolate. So now we can have an intramolecular reaction, and the potential intramolecular reaction would be between the carbon of the enolate, and it would potentially try to react with this ketone, or it could be the carbon of this enolate, and it would react with this ketone. Just to note, you could have deprotonated either side of this ketone as well, but it would actually give you the exact same situation due to the symmetry of the molecule. It ends up being, there's a plane of symmetry. So now we need to compare what happens if we try to do either of these. If we tried to do this reaction, it actually ends up not working out very well. So going in one direction, we're going to connect this first carbon. We're going to call that 1, 2, 3, 4. That means we're going to make a 4-membered ring on one side. Then we have a carbonyl. This attacked a ketone, so we'd end up with a minus. Then we need to count the other side to figure out what is the size of the ring that follows. So this is 1, 2, 3, 4, 5, 6, 7, 8. This ends up being an 8-membered ring. So 8-membered rings look kind of like a stop sign when you draw them. Oh, I even missed one. I think. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So you get something that looks like this. So this is not favorable. This actually wants to go backwards because the four-membered ring is really strained, and that'll just go back. It's actually very hard to make four-membered rings. Hard to. Now, if we consider this other approach, we can do the same sort of logic and try to count the ring size this way. So as we're going to have this carbon react with this carbon, we can number it as 1, 2, 3, 4, 5, 6, and going in one direction. And so this would end up with a 6-membered ring. Now to the right of that carbon will be the ketone. And we can use a different color. We can draw the going in the other direction. So we still will have this as being 1, 2, 3, 4, 5, 6. I think the counting and keeping track of everything is definitely the hardest part. We have the ketone that results because the electrons will also come down at the same time. I didn't draw those arrows before. And this is where the ketone was, right here at 6. So this is carbon 1. This ends up being carbon 6, either way you number. And this is the O minus. Now this is going to go through proton transfers. And I drew it up here, I guess, again already. So if you can see that there's going to be a hydrogen here. So this alcohol gets protonated, then this hydrogen gets deprotonated, then you can do the E1CB to go up. So the bigger ring, this, was that a 10-membered ring? It actually helps the reaction because it's an intramolecular reaction. So this is actually called a transannular reaction because it's reacting across the ring. I would say that this one probably would be too tough to put on an exam, but it depends on the ring size. You can definitely make, I think it's more about what the resulting ring sizes are. So if you start making very small ring sizes, that ends up being pretty bad. You could make a 6-5, that would still work without any problems. Depending on the situation, you could also make from an original 8-membered ring react across to make 2 5-membered rings, and that should also be quite fast. Cool. All right. I'm going to go back to these problems. This is actually from the same question. This is now 25E. Only now we can use some of the chemistry we're a bit more familiar with, at least that we learned. And this would involve the reaction of an aldehyde and an ester. This makes our life just a little bit easier this way. Hold on, make sure I got all this stuff. I need to close this. Sorry. Day has been a long day, but it's going to be great. Cool. And so if we need to synthesize this by acylation of an enolate, so we essentially have two options. We can either choose to break this bond, or we can choose to break this bond. Acylation means we need some sort of acyl donor. And while in the previous question, the best thing to use was probably an acid chloride, here we can use an ester without too much problem. So let's evaluate the blue option. This would get us back to making an enolate that looks like this. And an ester that looks like this. This is a pretty good situation because let's imagine we did this reaction with sodium methoxide. So we are making this enolate from the methyl ketone. We know that methoxide won't do transesterification. on the side of the ester over here. Even if you deprotonated this ester, we wouldn't get homodimerization. We know that ketones are fairly slow to homodimerize, so you could pretty safely add in methoxide, make this enolate, and the only thing it would be able to do probably is go and react with the ester. And this would go through a similar attack to give a tetrahedral intermediate again. And this would collapse to kick out methoxide, and you'd get the product. If the ester enolized, it can't do much. I think this was the example in class of the exact example in class of the ester that does not have a favorable equilibrium. So this potentially could happen with methoxide, but reacting with itself favors the reverse stage. Yes, this would still need to do an acidic workup at the end. So I am not explicitly showing that after this tetrahedral breakdown, we're in basic conditions, we're going to be deprotonated, and then it'll need to be protonated again. That is a good comment. Well, let's look at the other option, just because we can. So then we'd end up with an aryl methyl benzoate and try to make, and this would be pretty safe too, because no matter how you make this enolate, if you try to use LDA, it'll deprotonate in the right place. This hydrogen on the other side, even if it tried to add into itself, the reverse process would be favored in the equilibrium until you get the product you want. So this would be able to do the same sort of attack to make these molecules. But again, these types of acylation of enolates we haven't focused on as much. Most of what we're looking at will be alkylation, I think, to do those problems. So they'd be more familiar with what you've seen in the past. We go over number 3 on the practice exam. How do we pick between A and D? So if we're trying to compare which one is the least nucleophilic, you can generally rely on neutral compounds being less nucleophilic than charged compounds. There is maybe a bit of overlap in some very specific scenarios, but I would say that this is something you can kind of rely on. If you go to an exam, you see, what is the most nucleophilic? All the neutral things will probably be wrong. If you look at which one is the least nucleophilic, all the charged ones will probably be wrong. So I would quickly get it down to A and C and go from there. Between A and C, I think it comes back to electronegativity. Oxygen likes to hold on to its electrons much more tightly, whereas nitrogen is less electronegative and it's pretty happy and so it will be the better nucleophile overall. Amines are much more basic and nucleophilic in general. You can go and make a quaternary ammonium salt through reaction with a neutral amine with an alkyl bromide, but an alcohol doesn't do that without base. Cool. This is one similar to what they're asking us show how each of the following transformations could be accomplished. You can use any other required reagents. So one thing we want to see is, did we add any carbons? So that's never a bad thing to check out. So let's start numbering them. Say 1, 2, 3, 4, 5, 6, 7, 8. This has 1, 2, 3, 4, 5, 6, 7, 8. So in the end, we didn't gain or lose any carbons. We can actually see how this molecule kind of maps onto one another. We do have a change in oxidation state somewhere where this alcohol probably used to be this ketone. We both have them as labeled as number 2. And we see this bond form between carbons 7 and 3. That means that somewhere it looks like we're going to have a nucleophilic attack of carbon 3 on to ketone number 7. So if we were to treat this initial compound with just sodium hydroxide and heat, we would first make the enolate. Because of the symmetry of the molecule, deprotonating either 3 or 6 are actually, they're identical. You can see how this enolate comes down. It'll attack. If you wanted a number, just make sure you're making the right sized ring. It never hurts to count again. And I like to start from the carbon or the ketone. And we are making a 5-membered ring. So we can go ahead and draw the 5-membered ring. We had our ketone attack. And we end up with this O minus. I don't like that bond. Draw my squiggly methyls. Now we're going to do a proton transfer. I'm just going to say proton transfer. Oops. Proton transfer E1CB. If you're on an exam, you should definitely write out the E1CB. But for the sake of time, this gets us to this methyl ketone. Oh, I lost my carbon along the way. I'm sorry. And this can go to the product with just sodium borohydride. No questions on 1935. We're going to jump back again. Damn. Which of the following compounds is the least acidic? Could you? I've gone through this, I think, a few times. Is there a specific question about this that you have that I could focus in on? Is it the element of it? Why is an ester less acidic than a ketone? Or I'll still copy it and talk about it. I just want to make sure I'm hitting on the right. Okay. Yeah, so I think from this problem, if you're in the exam, and it's actually which one is the least acidic, we can probably very quickly get rid of E, C, and A. These all have alpha hydrogens in between 2 carbonyl groups, and these will always be more acidic than a single carbonyl. The case of acidity for an ester versus a ketone is a bit more challenging. So let's draw it out. Let's imagine adding in a base and making this. We get an enolate. And in the case of a ketone, we also make an enolate. Oh, I drew an oxygen again. Let's start over. So from this perspective, they look pretty similar. There's a couple ways to rationalize why the ester is a stronger conjugate base. One way to think about this is you have an extra donating onto that carbon that makes it more nucleophilic, but that's kind of hard to see. One way to rationalize this, though, is what is lost along the way when you have an ester going to its conjugate base? Before the ester was deprotonated, the lone pair on the oxygen of the ester was able to resonate into the carbonyl of the lone pair of the oxygen was able to resonate into the carbonyl. And so this resonance structure gives it stability. Once you deprotonate this molecule, this is actually some stability that you lost along the way. So actually, the reverse process is more favorable relative to a ketone because we would get this resonance interaction back. Note that now this oxygen can donate to this carbon, but making a carbanion is not as good. The ketone doesn't have the same penalty. It can just be deprotonated and make an enolate. So this is similar to the idea of ground state stabilization, where this is a situation where it's almost better to look at how the starting material changed when going to the conjugate base, rather than just looking at the stabilizing features in the conjugate base itself. Because it's this resonance that was lost that ends up making it less acidic. Because you can draw similar types of resonance structures both for the ester enolate and the ketone enolate. Does that help out at all in trying to think about this? Of the ones listed here, the most acidic would be A. So these types of things are additive. So since ketones are more acidic than esters, a diketone will be more acidic than a ketoester, and a ketoester will be more acidic than a diester. Yeah. And even if some of these explanations don't make sense, in order to answer these problems, I would say remember that electron donating groups into carbonyls make the alpha protons less acidic. And so similarly, if you had something, where do you guys think an amide would be in terms of acidity? We compared these three groups. Yeah, so an amide will be less acidic than a ketone. Will an amide be less acidic than an ester? Yeah, so if we go back to the idea of along the way, if we imagine deprotonating an amide, we're going to have a very nucleophilic conjugate base. And we lose this really an even stronger resonance interaction along the way. This nitrogen used to be able to go and donate electrons into the carbonyl, and it can't do that in the enolate form. So that means amides will be even less acidic than an ester. There are some general themes there. I'm going to climb my way back up. Let's see what question I had next. How in the world do you do this? Oh, I know how to do this. Cool. So they say you may use any of the required reagents. But you can actually, this is similar to one of the problems that I could be asking. These are the types of things I like, where you can make the product from 2 times the starting material. So again, it's always useful to, I think, to go and maybe map out. So we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. Now let's switch to another color. 1, 2, 3, 4, 5. So now we can get a sort of idea we can imagine how this was made right there with this bond. Here we had an oxidation state change. So it used to be our aldehyde. And if you were to take this starting molecule and also heat it up with sodium hydroxide and heat to do our aldol condensation, it will make this compound, which is almost already there to the product. We just need to go and treat it with sodium borohydride. And of course, a workup. So I think a lot of these questions, whenever you start with an aldehyde, and if you notice, I think already on the template that I put up there for the next exam, you will have problems where I'm going to give you explicit starting materials, and you either need to use the same thing multiple times to build it up, or you have to use the fragments that I provide. So similar to the problem set in that respect. So I think the approach to those should be familiar. I don't think someone else has asked for a different question. We just did number 1. We did number 3. Okay, I can keep going on the last question on Piazza. So for this first reaction, we can note that this methylamine is a soft nucleophile. So it's going to use its electrons to do an aza-Michael addition. This is a 1,4 addition. At first, this will give us a charged intermediate that after proton transfers will get us to putting one of these alkyl groups on. This process just repeats one more time. So hopefully you can see that without me drawing the intermediates. It'll be the same attack and proton transfer. We can do problem set 10E. Yes, we can. And then we treat this with base, and we don't know what base, but there's only really one type of proton that's acidic. We'll make this enolate. I'm drawing the carbon form just so I don't redraw everything. And we'll see that if we start counting, this is 1, 2, 3, 4, 5, a 6-membered ring will form. We make the tetrahedral intermediate. This is able to collapse. And we'll make the product. Most likely this intermediate would have been deprotonated and you'd need to use acid again. But it looks like the book was not explicit on the workup. Why doesn't the nitrogen add 3 of the unsaturated carbonyls? Oh, so that would be a pretty reversible reaction. You'll usually only see amines. It's a good question. How can I explain this? Okay, I'll explain it this way. Part of the reason is the reversibility. Note that whenever you have this step here, we have a proton transfer that allows you to deprotonate the nitrogen and take that charge away. Here, we never really have a stable leaving group. It's the negative charge is always attached to the molecule, so it'll prefer to just go backwards. Things are a little different with alkyl halides because the corresponding counterion is so stable. Like a bromide or a chloride or an iodide. In this case, our counterion is an ester enolate, so that's much higher in energy. So we can make this briefly and then proton transfer to go back down in energy. But if you try to do this another time where we had, I'm going to just draw maybe triethylamine to show as an example. But some sort of tertiary amine. And I think this is what you're asking. Correct me if I'm wrong. I believe if you had some tertiary amine add in, this couldn't exist and be stable. This would always very much favor to go the other direction and go backwards. Is that what you were asking? I hope so. Yeah. A good question, though. Moving along. Problem set, question 10E. E. Okay. So for 10E, you actually didn't need anything from this topic. More or less trying to come up with more questions for you to do. So the main idea is somehow we need to make a double bond and we need to get rid of an oxygen. And the bigger question is we need to introduce this ethyl here where the carbonyl is. So this would probably, a reasonable thing to consider here is we need to go and have some type of carbon nucleophile attack the ketone. So that could be something like ethyl lithium. After aqueous workup, we're going to get out this tertiary alcohol. And now in order to go to this double bond, we can use some sort of acid, H2SO4, to protonate this alcohol. This will go to the carbocation and it'll eliminate to the most stable double bond, which is certainly this tetrasubstituted olefin. If you go over number 13 on the practice exam again, I'm confused about how the OH eliminates without heat. Let's go take a look. This is indeed one of those cases where it will always be eliminating, and that's because this hydrogen right here is very acidic. Yes, I can do that. So whenever you have the 1,3-dicarbonyls, these will eliminate the alcohols through the E1CB mechanism all the time. The slow step is actually getting the first intermediate deprotonated to get into a high enough concentration to kick out the hydroxide. So if you have something that very easily makes its enolate form, the hydroxide doesn't stand a chance and it'll go away. But yeah, I can go back and answer some more questions here. I can draw this out a bit more. So if you treated this with sulfuric acid, this can be protonated by the alcohol. We'll turn the alcohol into a good leaving group. This will leave on its own because we can make a very stable tertiary carbocation. And now usually we'll deprotonate the molecule. All the hydrogens next to a tertiary, or all the hydrogens adjacent to a carbocation become crazy acidic. So our sulfate is probably our best base around. Could be the water molecule you just formed. And that'll go back down to give the product. And generally, whenever you have strong acids, we'll end up getting the thermodynamic product out, which is the tetrasubstituted olefin. So sodium hydroxide is not very good for getting this elimination to work here, because we haven't turned the OH into a good leaving group. The only thing you can really do with hydroxide is deprotonate the alcohol. And this would be a reversible equilibrium. In the case of enolates, where we've seen the OH eliminations again and again, it's because we have a CH bond that is sufficiently acidic to be deprotonated to get us to go to the enolate. And it's the fully deprotonated conjugate base that eliminates the hydroxide. We would never be able to deprotonate any of these hydrogens with just sodium hydroxide or really any other base. So we won't be able to see the elimination of an alcohol under basic conditions on simple alcohols. They really need to have the carbonyl group next to them. Yeah. Usually because they're neutral. Most neutral nucleophiles, except water, are soft. And water's kind of weird. We don't ever talk about water in that context because it doesn't even do the reactions that where it would enter the discussion. So soft nucleophile children are things that have fairly low energy electrons. So it means it's an anion that is very dispersed and stabilized, or it's on a neutral atom where they're moderately diffuse and available. Is that one of the ones that I had written, or is this a new one from the book? Just so I know where to look. Oh, it's new. Okay, then let me open it up. On the whole, malonates are just really easy to alkylate. Keep going. The question was revolving this double electrophile. I believe we used a malonate ester synthesis to make, or acetic ester synthesis to make it beforehand. Where these are bromines, not benzyls. And the question was using versus acetone. You could do it with acetone. I can't think of a reason why in this class that would ever be wrong. Because using the other methyl afterwards would actually make an awkward ring size. It would make a 7-membered ring, which would be less favored. For practice exam 12B, could you use an amine instead of a cuprate? No, you'd really need to use a cuprate here because we're making a carbon-carbon bond. And there's not a nitrogen in the product. So if you added an amine into this compound, you would end up with something that would look like this. Whatever R2. So you need to have the nitrogen there. Out of curiosity, is there a general trend to follow for figuring out the relative acidity basicity of other major groups we have studied in the topic? I just wrote right before class a pretty long Piazza entry on someone asking. I'll try to find some other, I mean, I've discussed how to approach these problems a number of times in a number of, I think, lectures and office hours. Generally, you want to, if you're looking at how acidic something is, you'll want to consider the stability of the conjugate base. If something that has a very stable conjugate base means that the initial starting molecule was very acidic, then the elements we're looking to determine stability involve electronegativity of the atom it's on, hybridization of the atom that it's on, and any sort of resonance stabilization that could be taking place. And that can include things like aromaticity. There's a few instances where we actually need to go back to the starting material a little bit more and see, did we lose something from going from the starting material to the product? So in the cases where we lose aromaticity along the way, or we lose a strong resonance interaction, this will also decrease either the basicity or acidity, because it wants to kind of stay in its original form. And I made a note of the things for this section in particular to kind of probably keep in mind, because the question I would ask is probably still going to involve some sort of acidity of alpha carbonyl compounds. If there is a problem with an ester, you should always use the alkoxide of that ester. If you use sodium hydroxide, you're going to hydrolyze the ester to a carboxylic acid, and you probably won't get the product you want. Because then you won't be able to make the enolate, because you can't make dienolates and carboxylic acid enolate, which would be a dianion very easily. Yeah, so potassium carbonate will deprotonate a carboxylic acid to the carboxylate salt, and that does an SN2 reaction. And if you've ever seen adding acetic acid to baking soda, and it creates all the carbon dioxide, if you use the bicarbonate base to further deprotonate again, then you end up losing CO2, so this becomes a largely irreversible reaction. You could also use something like sodium hydride if you want to. All right, cool. There's no more questions. I'll let you guys go. Hope everyone does well tomorrow on the exam. Adios.